Hi everyone, so we're just going to look at some questions relating to this week's assignment. So that's assignment 6. So all the questions I'll work through will be from this week's tutorial and assignment sheet, and I'll just work through the solutions to some of the problems on the sheet, and hopefully that'll give you a better idea of how to do the actual assignment questions. So we're still looking at integration in this assignment, but we're looking at slightly more complicated integration techniques. And so let's just make a start. So this is part A. So what we want to do is we want to show that this is equal to this, right? So we want to start off with this part of the equation and we want to end up with this as our answer. And these are things that are going to help us along the way because we're going to need to use an appropriate substitution and we'll take x over a as our u, right? So we start off with this thing first. So we want to kind of manipulate this so that it kind of starts to look like this, and that'll allow us to go from here to here in the context of our actual question. So what we want to do is we want to first things first factorize out this a squared so that we can have a 1 in there somewhere. So that's what we'll do first. So when we factorize out that a squared, we'll have to divide the minus x squared by a squared as well to still have the same thing happening in our actual question. So then because our a squared and this term here are terms that are multiplied, right, we can sort of split up the square root for each of those. So it'll be like this. So because both the x and the a terms are squared, we can just write it with like a single squared instead of having like 1 for the x, 1 for the a. So we can just go x over a squared. So now is where we would make our substitution. So we're going to take u as x over a. So this is our u. And because we're going to deal with things in terms of u, we also need to change this dx to be something in terms of u. So if we just do this over here, so if our u is x over a, then if we differentiate that, so du over dx, so we're differentiating with respect to x, we're just going to get 1 over a. And then if we make dx the subject, we're just going to have a du. And then if we substitute all of that down here, we're going to, and if we take this 1 over a outside the integral, because a in this question is just like a constant, it's just a number, we're going to have something looking like this. and then these a terms will cancel, and we'll have this. So as you can see that this looks kind of similar to this, right? So instead of an X, we've got a U, right? So our answer will be something in terms of U like this. So just to avoid me having to erase this page, I'll just kind of do the rest of the answer up here. It's a little bit messy, but we'll just... So using this idea then, right, that is equal to sine inverse of U plus C, right? So here we have an X, so it's going to be sine inverse of X, but here we have got a U, so it'll be sine inverse of U, right? So don't forget the plus C, and then we can't leave our answer in terms of U, so we just replace what we took for U back into the question or to get our final answer. All right, so we've shown that we can start with this and end up with this, right? So that's how you do this question. I'll just clear the screen and we'll move on to looking at the next question. So part B, so this is question 2B, is still using a similar sort of idea to what we did in part A. So in the question, we're given the following. So that was sort of what we were given in part A, but you can still use this idea for part B of the question as well, right? And we are trying to find this. And we've also been told, just write it up here, that 5 minus 12x minus 9x squared is equal to 9 minus 3x plus 2 squared, right? So the first thing we'd do is we'd go and replace this with what we're given in the question. So again, we're trying to do the same sort of thing that we did for part A. We're trying to manipulate this, right, so that it sort of looks sort of similar to what we've been given in the question so that we can go from the integral to our answer, right? So what we do here is we kind of need to work out what our A value is, right? So that's the first step. And we then also need to decide on what our U will be, because you still need to use an appropriate substitution for this question as well. So sort of doing a similar thing to what we've done in part A. So 9 is the same thing as 3 squared, right? So in this context, 3 is like our A value if we sort of compare it to what we've been given up here. And then we've got the 3x plus 2 squared still there. So to kind of get it to look like this, we can make this our U, right? So I'll just do it over here. So we let U equal 3x plus 2, right? And so because we're going to eventually be working with everything in terms of U, we want to replace this dx with a du term as well, right? So we want to be consistent. So if we differentiate this with respect to x, we'll get 3, and then dx is just going to be du over 3. Okay, so if you put all of that into here, we'll end up with something like this. So because the 7 and the 3 are just numbers, we can bring it outside and we'll have something a lot neater inside the integral sign. See. So then we've sort of got something here that looks like what we've been given at the start. So then from this, we can jump straight to this, right? So 7/3 stays as it is. So in this question here that we're working with, our A is 3. So we need to obviously make sure that we replace that in our final answer. But if we just go from here to something like this, we'll get the following. So it'll just be sine inverse of u over a plus c, because we're working with u and not x. And then if you replace u and a in your final answer, you should end up with something like this. Right, so that's just plus c on the end there. So that should be what you end up with as your final answer for question 2b. All right, so I'll just clear the screen and we will move on to looking at question 5. So in question 5, you want to evaluate those integrals that are sort of in this particular form here. So right, so if you refer to the lecture notes, you'll see that things in this sort of form can be integrated as follows, so like this. And so this is the general idea that we're using for these questions, right? So these equations are in your notes, so they're in the lecture slides. So if we look at 5a first, so based on this kind of form here, we obviously need to decide on our f of x and our f dash x. So generally the denominator, right, is your f of x. So our f of x is x squared plus x plus 25. And then f dash x, so we differentiate that, we'll end up with 2x plus 1. Right, so obviously 2x plus 1 is not the same as what we've got at the top, right? So that's where this alpha comes in. It's just a constant that's multiplied to the top of your fraction, right? So we can see that if we multiply 2x plus 1 by 2, right, we'll end up with 4x plus 2. So that kind of means that our constant term, so our alpha, is equal to 2. And then based on that, our f dash x, or alpha f dash x, the top part of our fraction, is now just 4x plus 2, right? So working out what that constant is important when it comes to working out your final answer, right? So based on all of that, we can say that, actually, I'll just do it over here to avoid writing that out again. So if we integrate that, we'll end up with 2 ln of x squared plus x plus 25 plus c. So we've just basically put everything into this equation up here. And the reason I said that finding that alpha, or that constant value, was important because you need to multiply it to your final answer, right, to get it in the correct form, right? If you didn't have that 2 there, you wouldn't have the right answer. So just using this kind of approach to work out what that constant value is quite useful. So that's question A, and question C is also fairly similar as well. So I'll just clear the screen and we'll look at that one. So this is question 5C. So we're still using this idea here with our new question, right? So question 5C. So for this one, it's kind of useful to use the table of derivatives, and think that's given in the lecture notes. So table of derivatives. So that's kind of useful to work out what is your f of x and what is your f dash x. So if you look at your table of derivatives, you'll have your f of x column there, and then you'll have your f dash x column there, right? And then you can find tan inverse of x on this side, and that corresponds to 1 over x squared plus 1, right? It's given as 1 over 1 plus x squared, but it's the same thing, right? So based on this, right, you can see that in our question, our f of x is tan inverse of x, and our f dash x, so the derivative of that, is our 1 over x squared plus 1 term, right? So that's over here. And then based on that, so for this question, unlike for 5A, we don't have any constant term that's multiplied to it, because the top and bottom parts of our fraction here are exact, right? We don't have it scaled by any sort of constant like we did in part A of question 5, right? So that's all we need. And then all we do is we just, I'll just write this out again. It's just use this information in this equation and put everything in. And that is our final answer. Let's see. So I'm just going to clear the screen and we'll look at question 6. So with question 6, again, there's the questions that we've got there. So the integrals are in this particular form. And if you refer to your notes, there's a formula given. So this is in the lecture slides that looks something like this. And this is particularly useful for working out the answers to these questions. Apologies for the barking in the background, that's my dog, but hopefully you can still hear me clearly enough. So this is the idea that we're going to be using for these questions. So if we do question 6A, so which is so similar to question 5, you need to decide on what your f of x and what your f dash x is so that you can write out your answer appropriately, right? So in this case, our f of x term is ln of x, because if you differentiate that, right, you're going to get 1 over x. So this is the same thing as ln x times 1 over x, right? So this is like your f of x and this is your f dash x. And then that's pretty straightforward, right? We don't have any constant term to worry about because they're exactly, they exactly differentiate to each other. So ln x and differentiates to 1 over x, and you don't have any sort of constant term that scales your answer by any amount, right? So it's just exact. And then based on that, if I can just sort of fit it in over here. No, I'll just write it here again to make it look neat. So if we just put everything in here, our answer is going to be half right? So it's half ln x squared plus c, right? So don't forget to include the plus c, right? It's a common mistake to forget the plus c term. So we'll look at question 6c as well. This is just to remind us what we're doing. So if we look at this, we need to pick a f of x and an f dash x, right? So if you again refer to the table of derivatives, like if you don't already know this offhand, it'll kind of help you to work out which should be our f of x term and which should be our f dash x term. So from here, we know that tan x, right, that differentiates to secant squared x, right? So based on this idea, this is our f of x and this is our f dash x. But we kind of need to modify it to suit our question because we've got these a terms in there, right, which are like constants, right? So using this idea, we've kind of worked out that f of x is tan ax. And then if you differentiate this tan ax, right, we don't just have an x, we've also got that a term there, which is just like a number. So our answer is going to be a secant squared ax, right? Because you need to account for that number in there as well, right? And so because of that, right, this a is sort of like the alpha term in our question. So it's like, right, so it's kind of like this number over here that we kind of need to worry about when we write it in this form. All right, and so that means that our final answer is this. So that's the half term there, but because we've also got this a to worry about, right, we just divide by the a as well. So it's just 1 over 2a, and then our f of x term is just tan ax squared plus c, right? So it's just in some of these questions, right, you may need to find that constant, and that could just be something that trips you up if you're not careful about that. So yeah, that's all I've got for question 6. So next we'll just look at part A and part B for question 7, and that's all the questions that I've got. So with question 7, we're really just using integration by parts, right? In both part A and part B, right? To work out those integrals. So if we look at question 7a, but before we do that, it's really nice to have the integration by parts formula down so that we can sort of refer to it when we're working out the answer to our question. So that's the equation or the formula for integration by parts, which I'm sure you've seen in lectures, right? So with question 7a, we're trying to integrate x to the a ln x dx, right? So this part is sort of the same thing as this part on our, well, in our equation here for integration by parts, right? So we're wanting to integrate this using integration by parts. So based on this equation here, we want to work out what our u and what our dv terms are, right? So sometimes the tricky thing is deciding what you should take as your u and what you should take as your dv. But generally speaking, u is something that you can differentiate and your dv term is something that you can integrate. So the obvious choice here for u would be your ln x, because you can't integrate it as easily as you could integrate x to the a, right? So if I just write it in this way, so it sort of matches up with our equation there. So this is our u, and this whole bit term here is our dv term from this part of our equation. So we need to find a v, and we also need to find our du. So if our u is ln x, then if we differentiate that, du by dx, that's going to be 1 over x, but we want it to be like du equals something. Whoopsie, sorry about that. So hopefully you can still read that, but du is going to be dx over x, and then if we look at our dv, right, so dv was x to the a dx, this part here. So to get v, right, we want to integrate dv, but because we're integrating this side, we also need to integrate that side as well, right? So if we integrate dv, we'll end up with just v, and if we integrate this, right, it'll just be x to the a plus 1, right? So a is just a number, so if you integrate, you just add 1 to the number in the power, and then you divide by that new power. And so that there is our v. Maybe I will do the rest of the question on a fresh page because we're going to run out of room. So I'll just write this back up here again. So we wanted to integrate x to the a ln of x. So that's that part here. So now, based on what we found just before, based on our choices of u and dv, we just go through and replace the appropriate terms in this side of the equation, right? So our u was ln of x. Our v, which we just found by integrating this x to the a term, was x to the a plus 1 over a plus 1 minus the integral of v, which was this. And then our du was dx over x. that's just tidying this up a little bit, right? So what we can do here is that we can cancel out this 1 over x term. So we can cancel out that x, because if you cast your mind back to that power rules that we looked at a really long time ago in like one of the earlier assignments, if you've got like 2 powers to the same base and then multiplied together, right, you can add them up. So you can do the reverse. So you can sort of split it up as x to the a times x to the 1, or just x, and that's 1 over x. And so that'll allow you to cancel those x terms so that we can simplify what we've got here before we actually integrate. So we're not really doing anything to this part here. It's just staying as it is. We're really just concerned with this part here because that's what we want to integrate. So after we've done that, it looks a lot tidier. It's just x to the a over a plus 1 dx. So that's a lot easier to integrate, right, compared to what we had over here. So, do remember that you can use those power rules to help you simplify down your integral before you actually integrate it. So the next step is to just integrate this here. So this part, remember, just still remains the way it was. Nothing happens to it. So we integrate in exactly the same way. So that's going to be x to the a plus 1. You add 1 to the power and you divide by a plus 1 as well. But because we've already got an a plus 1 here, it's just going to be a plus 1 squared, right? Because you've got that a plus 1 and then you're dividing again by a plus 1. So you'll have like 2 lots of a plus 1 at the bottom. And then don't forget your plus c term. Okay, I'm just going to continue with this on like a clean page because you can simplify your answer down a little bit more. So if we just continue on from the last thing that I wrote up, right, we've got x to the a plus 1 ln x just write it out again so that we know what we're talking about, right? So we can sort of factorize out the common parts over here. So the x to the a plus 1 on the top is common for both of those, and the a plus 1 term is common at the bottom for them both. So we can factorize that out. And that is your final answer for your question, right? So we'll move on to looking at part B, and we're doing the exact same thing. We're using integration by parts again, but we're considering part B of the question now. So let's just write down the equation for integration by parts so that we can match up the terms in our actual question. So we want to integrate x secant squared x dx using integration by parts, right? So this is kind of that, right? So we want to choose our u and our dv terms. So remember, your u should be something that you can differentiate easily, and your dv term should be something that you can integrate easily. So in this case, our obvious choice for u would be x, right? Because you can differentiate that quite easily. And then our choice for dv would be this here. All right, so based on our choices of u and dv, right, we want to find the remaining terms, right? The v and du terms. So if we differentiate that, we'll get 1. And then your du will just be equal to dx. And then if we look at our dv, so dv for us in this case is secant squared x dx. So again, if we want to get our v, we just integrate dv, right, to get v, but because we're integrating this side, you also need to integrate that side, right? So v is equal to tan x dx. So if you don't remember this offhand, right, it is in the table of derivatives. So this is the idea that we used for one of the previous questions that we've just looked at. So that table of derivatives is quite useful. So based on what we've got here, we just put everything into the integration by parts formula up here, and we work out what our integral is. And so another thing is that we've got this given in our question, which I forgot to write up just before. So we're given that okay, so we've been given in the question that if you integrate tan x, we end up with negative ln of cos x plus c, right? So that's given in the question. So based on that, right, it can kind of be useful to help you decide what you would choose as your dv to begin with, right? Because remember, your v should be something down the track that you can then again integrate. So if you're given this in the question, you should kind of know that this could be your v term, right? So just to help you out at the start a little bit. So if we go ahead and integrate, so if you put everything into this equation, we've got x tan x minus integral tan x dx. So we've been given what that integral is in the question, so that's just up here, and you can just substitute that in. So because we've got a negative and we have a negative over here, that becomes a positive, right? So just be careful with negative signs. And so you'll end up with this as your final answer. So in terms of the tutorial problems, that's all I've got for today. So hopefully you did find this session or this recording useful, and hopefully you can have a bit of a better idea about how to tackle the actual assignment problems based on what we've covered in the recording.